Hello, I welcome you all in this course on mechanical measurement systems. Today we will discuss the second order system, and mainly we will focus on step response of second order systems. Now, in the second order system, first we will deal with the basics of the second order system. If you remember the generalized governing equation for dynamic response of measuring systems, in that equation, if the degree of differential in output, that is of second order, that is A2 d square, d square QO by dt square plus A1 dQO by dt plus AO QO is equal to BO QI. So this type of system, the system response of the system governed by this equation are known as second order systems. Now on this side we can go for the higher orders. Not necessarily we have to restrict for BOQI only, but for all engineering uses, common engineering uses, this up to this it is good enough to represent many of the engineering systems, especially mechanical engineering systems. Right? Now here there is a term sensitivity of the instrument, and sensitivity of the instrument we get by dividing BO by AO. In dynamic response of the system does vibrate also. I mean, in first order system, the response of the system like this, the moment you give the input, the output will slowly rise and will become close to the input. But in dynamic response of the instrument, it is possible that there is an overshoot in the output, and after certain oscillations, the system gets settled. So vibrations are also involved in this type of system. That is why undamped natural frequency of the system is also taken into the account. And undamped natural frequency is equal to AO by A2. This AO divided by A2. This is undamped natural frequency. Now in the same, suppose a system is vibrating in air. Air will produce some damping effect, right? And not only air, even suppose a shaft is rotating with a certain speed, all of a sudden the power is stopped. The shaft will also stop after rotating after a certain period of time due to damping by the lubricating oil. So a damping ratio, it is normally represented by zeta. It is known as damping ratio. So the unit of this is radians per second. Now damping ratio has unit of Newton meter per second. So the damping ratio is defined as A1 divided by 2 under root AON A2. Now why I am doing this, I will be explaining you later on, because these three terms, because this equation, because A2, A1, A2, AO and BO, for any instrument they are not known to us. For any measuring instrument, let us say for example voltmeter, I do not know what is the value of A2, A1, AO, BO for voltmeter, but definitely for a voltmeter I know the value of K, sensitivity. WN also I can find out, natural vibration frequency, and damping ratio is also given. For dampers, the damping ratio is also given. So these are normally known quantities. So now we will replace, we will be putting these quantities here, and the expression we are going to get now omega n is equal to under root AO by A2. So if we divide entire equation by AO, so here we will be getting AO, here we will be getting AO, here we will be getting AO, and here we will be getting AO. Right? Now this is omega n. So we can write d square QO by dt square 1 by omega n square. This we will take later on. Here BO by AO we can always say K QI. We have done this for first order system also. Now this AO by AO they will be cancelled out. QO. Now A1 by AO is remaining. A1 by AO. Now A1 by AO and zeta we have defined as A1 by 2 under root AO A2. This is zeta. So if we take 2 zeta, then 2 zeta is going to be equal to A1 by under root AO A2. And if we divide this by omega n, when we divide this by omega n, then it becomes AO and under root A2. Now these two will be cancelled out, and then we will get the value of A1 by AO. So to 2 zeta by omega n is equal to A1 by AO. So here we will put plus 2 zeta by omega n dQO by dt. So this equation has been modified by this equation. Now we can write that d square by omega n square plus 2 zeta by omega n d plus 1 QO is equal to KQI. Right? And this becomes the transfer function, because the transfer function is for transient response QO by QI t is equal to K by d square by omega n square plus 2 zeta by omega n plus 1. This is transfer function. For example, there is a spring balance. I'll give you an example of a spring weighing machine. There is a weighing machine. Let us take one example. There is a weighing machine, and it is a spring loaded weighing machine. So there is a vertical scale, right? And there is a shaft. On this shaft there is a platform, and shaft is mounted over a spring. Normally it is assumed that it is a weightless spring if spring has weight comparable to the applied load, then 1/3 weight of the or mass of the spring is added, right? So now this shaft has divisions, though this vertical scale has divisions. So when the force is applied, the spring get compressed, right? And we get the output. So input, if it is a second order system, the input is Fi, input force. This is transfer function, K by d square by omega n square plus 2 zeta by omega square and d plus 1. Omega n d plus 1, right? And then it is XO is the output. So now if we know this transfer function, we can immediately get the value of output for a given input. So this transfer function will be directly transferred. So we'll get the output for a given input. Now we'll start with the force balance here. For the second order analysis, we'll start with the force balance. And this force has frequency well below or well above, or sorry, well below the natural frequency, not well above, well below the natural frequency, so that there is no interference. So there is no, this F force has frequency well below the natural frequency of the instrument. So frequency of F is well below the natural frequency of the instrument, and spring is weightless and it is linear, right? Now in this case, if we do the force balance, then force is equal to, sigma force is equal to mass into acceleration. Now sigma force is input force minus this. Here we have assumed that there is an air film, otherwise these machines are well lubricated. So damping of lubricating oil also becomes effective here. So when the damping of lubricating oil becomes effective, then it is B dxo by dt, right? This will resist, this damping of the lubricating oil will resist Fi. So it is opposite direction minus kxo, spring, force due to spring. This is the sum of the forces, is equal to this, let us take capital M. So total M into d square xo by dt square. Now we will rearrange these terms and we will get M d square xo by dt square plus B dxo by dt plus kxo is equal to Fi, input force. Now simply we will divide this by K, stiffness of the spring will be represented by S, stiffness of the spring, because stiffness of the spring is, so sensitivity of the instrument is 1 by Ks. This is the sensitivity of the instrument. So further we can modify this equation as M d square plus BD plus 1, this is Ks. Now we have not divided it by Ks, so it has to be like this. So plus Ks is equal to Fi. Now this is the differential equation for second order system, for this type of system. And now we want to have the value of xo multiplied by is Fi. Now from this equation, if you compare with the original equation, we can find that K, static sensitivity K is 1 by Ks, right? And omega n, natural frequency, is under root Ks by M. Ks by M. Because when the entire equation is divided by Ks, so this will become M by Ks. M by Ks is equal to 1 by omega n square. So from here we can get omega n is equal to Ks by M. And similarly, we can find the value of zeta as B by 2 under root Ks multiplied by M. So we have got all these three, and the static sensitivity, sensitivity of the instrument. Now, if we have high spring stiffness. If we have high spring stiffness, sensitivity will be low. Now here there is a very good observation that if this is high, the K will be low, sensitivity will be low, and here this is high, damping ratio will also be low. If this is high, this is low, this is high, this is also low. It means if we increase the stiffness of the spring, sensitivity of the instrument will reduce, damping ratio will also reduce. Reduction in damping ratio means the response will become quicker. So system will have quicker response if we have lower value of Ks. But at the same time, we will have to sacrifice the sensitivity. If we want to have very high order of sensitivity, then damping will increase and the response of the system will be sluggish. So a trade-off has to be struck between these two. Right? This is a particular case we have taken for spring balance. Now we will start with the step response of second order system. A generalized solution for the step response of second order system. As you know that in a step input, there is a change in the input from 0 to certain value within no time, 0 duration of time. And input is QIS and this is time dimension. This is step input. And if you remember for the first order system, we have drawn the characteristic curve for the response of the curve like this. And after a certain time interval, maybe 4 or 5 or 6 time constants or nearly 5 time constants, this become almost equal to this, right? So dynamic error is reduced to almost 0, right? But here in this case, the situation is different because here vibrations, we have considered the natural frequency also, and where, there is a frequency of the damped vibration also. All those things will be discussed here. First, we'll be discussing here. First of all, let us start with the basic governing equation for second order system. So the basic is d square by omega n square plus 2 zeta by omega n d plus 1 QO is equal to K QIS. Right? Boundary condition is same. QO is equal to QI at T is equal to 0. And so Q is equal to QI. And QI is equal to, and dQO upon dt, rate of change in output is also 0 at T is equal to 0. So at T is equal to 0, output is 0 and rate of change of output is also 0. These are two boundary conditions. Now here for finding out the solution, first is particular integral. So, and second is complementary function. Those two things we have to drive. So particular integral is, particular integral is QPI is, QOPI is K QIS and QO complementary function. For now we will have to solve this differential equation. It means d square by omega n square plus 2 zeta by omega n d plus 1. We have to find roots of this. Once we find the roots of this, then we will take the solution. QO complementary function is equal to, because D, there are 3 possibilities or 4 possibilities. First is roots are unequal and real. We will start with the first one. Roots are not equal and they are real. For that, the solution is C1 e raised to power S1t plus C2 e raised to power S2t. Right? So first of all, we have to calculate the root for this equation. And the root for this equation is, if you compare this with ax square plus bx plus c is equal to 0. In this equation, the roots are minus b by 2a plus minus under root b square minus 4ac divided by 2a. So if one root is plus and under root is minus. Now here b is minus 2 zeta by omega n. So minus 2 zeta by omega n. 2a is 2 by omega n square. So this omega n will be cancelled out, 2 will also be cancelled. So it will be minus zeta omega n. So this is minus b by 2a. Now the second part is b square minus 4ac. So it is going to be 4 zeta square by omega n square, that is b, minus 4 times ac, that is again omega n square, divided by 2 by omega n. This is 2 by omega n, 2a, 2 by omega n square. Now here 2 by omega n square, it is going to be further simplified as 2 by omega n square, 2 by omega n divided by 2 by omega n square multiplied by zeta square minus 1. So here this 2 will be cancelled, will be cancelling with this one, omega n with omega n1, and then we will be getting plus minus omega n under root. So the solution for this equation, we are going to have, there are two roots. S1 is equal to minus zeta plus under root zeta square minus 1 multiplied by omega n. The second root is S2 is minus zeta minus under root zeta square minus 1 omega n. Right? Now we have two roots. Solutions are not equal, they are real. Zeta is greater than 1. This is the case when zeta is greater than 1. And then we get solution as Q is equal to S1, sorry, not S1, C1, some constant C1 e to power st, S1t. So it is going to be minus zeta plus under root zeta square minus 1 multiplied by omega n t. And then we get again another one, C2 e raised to power minus zeta minus under root zeta square minus 1 multiplied by omega n t plus particular integral plus k q I s. So this is the generalized. Now we will be putting the boundary condition. Now boundary condition, there are two boundary conditions. Now the first boundary condition is at x is equal to 0, qo is equal to 0. This is q. At x is equal to 0, sorry, at t is equal to 0, at t is equal to 0, this is the boundary condition, QO is equal to 0. So we will be putting QO here, 0 is equal to, t is equal to 0, it means C1 plus C2 plus KQIS. Now another condition is derivative of these. If we replace this by S1, if we replace this by S1 for the sake of convenience, and this is S2, right? So if we differentiate this, then we get 0 is equal to C1 S1 plus C2 S2. This is S1. So when we differentiate this, C1 e raised to power S1, we will get S1, C1 e raised to power S1. And when we are putting 0, then this term will become 1. So we are getting C1 S1 plus C2 S2. Now we have two simultaneous equations. And if we solve these two simultaneous equations, we will be getting the value of C1 and C2. Right? So here we can say that C2 is equal to minus C1 S1 by S2. So this C2 is equal to minus C1 S by 2. So we will be putting the value C2 here. And when we put the value of C2 here, when we put the value C2 here, we get 0 is equal to C1 minus C1 S1 by S2 plus KQIS, right? Or C1 S1 by S2 minus 1 is equal to KQIS. Right? S1 and S2 are known to us. And then by putting the value of S1 and S2, we will get the value of C1. And similarly, we can get the value of C2. So this is how we can get the value of C1 and C2 by putting the boundary conditions. When in the original equation, the boundary conditions are put, we get solution like this. We say that the system is overdamped when the roots are real and unrepeated. And in overdamped system, this is going to be the governing equation. Now, another type of solution can be the roots are real and equal. Say for an equation ax square plus bx plus c is equal to 0. If I say the roots are real and equal, and roots, generalized solution for the roots is x1 and x2 is minus b by 2a plus under root b square minus 4ac by 2a. So here in this case, in such type of solution, if I want to have roots, equal roots, this has to be 0. So we are going to have minus b by 2a only. So in a critically damped system, the value of zeta is 1. So that is a critical damped system. And the value of input and output ratio QO by KQIS can be expressed by this equation. Now, the third one is underdamped system. When the roots are complex, I mean zeta is less than 1. This zeta is less than 1. When zeta is less than 1, then we are going to get complex expression in the so in that case, underdamped system, the final expression will be like this, k by qs, and for the value of phi, it is sine inverse 1 minus, so phi is sine inverse under root 1 minus zeta square, or it is cos inverse zeta, both are same. and frequency of underdamped vibrations, because when the system is underdamped, the system will vibrate for a certain time period, and this frequency of damping frequency of the second order system which is underdamped is natural frequency multiplied by 1 minus zeta square. Right? So now we have discussed all three systems. I mean, overdamped system, underdamped system, and critical damped system. The further discussions on these systems we'll have in the next lecture. That is all for today. Thank you very much.